Good afternoon, all. My name is Nicola Cairo, Project Officer at ETN Global. And today, on behalf of our office and team, we'd like to welcome you to the ETN webinar on the digitalization in turbomachinery, where we will explore the best practices and the state-of-the-art solutions with Paolo Silvestri from University of Genoa and Sébastien Grégoire from ENGIE. First of all, I would like to thank the Digitalisation and Diagnostic Working Group of ETN, particularly my colleague Giuseppe, who had the first input to start this webinar with the chair and vice chair of the Digitalisation Working Group, respectively Ian McAfee and Hugang Lee. So today the webinar will be as follows. We'll first have the presentation from Paolo Silvestri on the experimental investigation of incipient surge identification based on system dynamic responses analysis, followed then by the presentation of Sébastien on introduction to Robin, the historian for asset monitoring and a use case on vibration monitoring. So with no further delay, I would like to give the floor to Paolo. I would like just to make the final remark that this meeting is being recorded. You will receive the presentations from our office after the meeting. And also you will have the possibility to review the recording on our YouTube channel in the next days. Thank you also for attending. So Paolo, I would like to give you the floor. Thank you.
Thank you, Nicola. Good morning, everybody. I start with my presentation about incipient surge identification. The aim of this work is the analysis of incipient process and the origin of surge occurrence. To predict correctly surge is very strategic in complex plant as a fuel cell. So this topic is very strategic in the engineering field. The activity is a condition monitoring activity. We have a system, a compressor, and during operation, the system receive input sources exciting the system, mechanical sources as unbalance, fluid dynamic sources, and moreover noise, as we are on field in a real, not mathematical environment, but a real environment. The aim of this activity is classify an incipient surge condition observing a specific output from the investigated system, a typical condition monitoring problem. We had to consider that we can capture the output. In this case is the monitoring phase of a condition monitoring process. And then we have to interpret the data in order to classify the actual condition of the compressor. For compressor surge is important to collect data from the compressor itself, but not only. It is useful also collect data with coupled other component. For example, an electric-driven compressor, the identification of surge can be also detected by observing the output from the electric driven motor, for example. And so the output generally not refers only to the fluidodynamic machine, to the compressor, but all the coupled mechanism inside. Moreover, we collect the data, and then it is important to classify the condition stable, incipient, and instability condition. For this aim, it is very important to use correct signal processing technique in order to extract from the collected data the useful information for diagnostic purpose. Generally, signal processing technique allow to separate in the observed, in the measured output, the contents strictly related with the investigated phenomenon, in this case, the surge. For in our cases, it is very strategic to correctly separate in the measured signal the correct contents in order to improve the efficiency in detecting surge. So for interpret the data, it is very important to apply specific separation technique in the acquired measure. We had to take an account that compressor is a mechanical system, and in a mechanical system, the observable output are generally the mixture from contribution due to a lot of sources. So to improve diagnostics is very important to separate in the output the contents more sensitive to the surge rise. I wanted to show you some application cases. The first is related to an automotive turbocharger. In this case, the compressor is driven by a centripetal turbine. I show you surge detection using output captured by accelerometer, microphone, and inflow pressure sensors. In this photo, you can see a microaccelerometer on the left. Microaccelerometer able to detect high-frequency contents in the structural response up to blade pass frequency. Before surge detection, it is very important to define the stable signature of a system. As if we have a reference condition, we can consider the reference condition and detect the approaching surge by observing a deviation of a signature from the reference condition. And this slide put in evidence a stable condition in terms of acoustic pressure measurement and structural measurement measured with an accelerometer. Please note that the main sources, in the case of a centrifugal compressor, main sources are unbalanced subsynchronous component due to floating ring bearings characterized by whir phenomena, typical subsynchronous phenomena, and blade pass frequency are well detectable both with microphone and also by accelerometer. Also in this case, you can see spectra not during a stationary condition as the previous slide, but during a RNAP. In this case, we can see that Fourier analysis is able to separate the main sources present in the system in a stable condition, as we are able to detect the frequency contents relate unbalance, the synchronous one, blade pass frequency, and resonances. So frequency analysis, FFT, is able to well detect the main sources acting on the system. Now we can switch to surge identification, and I want to present steady test and transient test. Steady tests are characterized by constant reduced rotational velocity of a compressor at steady condition characterized by reducing of mass flow rate, so approaching surge line. Transient was conduced keeping the throttle valve in the feeding line of a compressor in the same position and increasing the compressor rotational speed, starting from a stable condition to an unstable one of a compressor. This slide shows the result in terms of microphone signal measured at the ambient condition at the compressor inlet. In this case, we have 5 spectra, and the frequency range is below the synchronous one. And please note, as a simple FFT is able to detect the surge approaching. Please note, we considered 5 conditions, 5 stationary conditions. The first, number 1, is the stable. Number 2 is the maximum efficiency, and then we reduce in a systematic way mass flow rate. And the last one, the number 5, please note my marker, is the last table before the rise of the surge. So subsynchronous energy in system response is good for surge detection, as its energy increase approaching surge. Please take in account that these are tested on at a specific test bench used for characterize compressor behavior. It is a conditioning environment. In real test, this frequency range usually is contaminated by the contribution from other sources, external sources of the complex implant. So this approach works fine in the low frequency range in laboratory test, but may be critical in field measurement. The same low frequency range is considered during the transient. In this case, we have a color map representation. The color bar is the energy of the frequency content, and the horizontal axis is frequency axis. Please note the compressor works at 60,000 rotation per minute, so 1,000 Hertz is the synchronous component. Here you can see exclusively the subsynchronous contents. And the vertical axis is the throughput time of the measurement of the test. And we are approaching as we are approaching a surge line. Please note as this energy improves in a significant way approaching surge. The same also from this. For another measurement. So subsynchronous range is good, but may be contaminated by other contribution. This slide shows you the system response in terms of vibration, so structural response, in the high frequency range, where we have generally no interaction with contribution from other contents. And this slide show free spectra. Free spectra from the top, middle, and bottom are spectra approaching surge. And please see my marker. We can observe the blade pass frequency. In this case, it seems that approaching surge, the impeller flux modify, and blade pass frequency reduce its energy if compared with the maximum efficiency condition. And on the side of a blade pass frequency appears other contribution. And what means that the previous subsynchronous contribution interact with an high frequency contents. It is a classical modulation phenomena. But if we observe the sideband of the high frequency blade pass frequency contents, probably is better. Is better as we are free from interaction with contribution from other sources, especially if we have in other plant. I show you another application. Our aim is to identify the surge. We considered also in this case a compressor turbocharger, and we use cross-correlation function. Cross-correlation function, it is a time domain function, and we use cross-correlation to separate in the measured output. In this case, we considered the inflow pressure signal. Cross-correlation allows to separate the deterministic contents from the random contents. As is known, cross-correlation, it is an operation that quantify the similarity between two signals as a function of a delay of one relative to the other. In the case of pressure signal, it's allowed the characterization and quantification of wave propagation phenomena in the duct by analyzing of a particular pattern in a sensor signal recurs in a second sensor placed a specific distance from the first. Near surge, significant pressure oscillation originates. And in this way, we want to detect the rise of this energy with cross-correlation. I want to show you this graph. This graph put in evidence as cross-correlation show a periodic trend, and the periodic trend is related to the deterministic content in the acquired output. And show a spike content. The spike content is related to the energy of the stochastic content in the acquired signal. This slide shows you the cross-correlation computation of a computer-generated signal. It is a computer-generated obtained with an harmonic contents and a white noise. Then I consider the second signal. It is the same, the delayed of 0.005 seconds. If I compute cross-correlation function, the spike is related to the random content, to the stochastic content. The deterministic trend is related to the harmonic contents in the original signal. So we used this method to separate in the acquired signal the random contents, and near surge random contents increase its energy. And in this case, please note the cross correlation obtained with two pressure sensor at the compressor outlet duct, as the scheme on the left. And the three figures show you the condition run number 2 stable, approaching surge, run number 3, and the last stable point before the surge line. Please note the presence of a marked spike. A marked spike, it is well detectable with reference to the deterministic content. The deterministic content is presence also in stable condition. And we have a lot of spike can be monitored and used as a feature for diagnostic identification. The last approach is based on kurtosis. Our aim is to acquire data and to separate in the acquired data the contents may be related to surge. In this case, spectral kurtosis is able to separate in the acquired contents the deterministic contents, the random contents, in this case, the random stationary contents, for example, Gaussian noise, and the transient random contents. Kurtosis is a statistical tool based on the moment of order 4, and is very sensitive to extreme event, so burst response, and in surge, extreme events may occur at low mass flow rate. The impeller flow incidence is not optimal, so a lot of burst response, a lot of energy in terms of burst response are present. Our approach is to try to separate the burst contents in the acquired signal. Generally, these contents is covered by noise or other contribution. So the approach based on kurtosis, and in particular spectral kurtosis, allow to explore the frequency acquisition band and obtain the optimal band pass filter which maximize the impulsiveness and the transient characteristic in the measured response. The final result is reported here. Please note the application of spectral kurtosis identify the frequency band more sensitive to burst contents, the one centered in the blade pass frequency, with a wide band equal to the range of the oscillation mass in the duct of the compressor. If we consider this specific contents of the filter signal, we note what is reported in this slide. If in this case we have not the filtered signal, but the envelope, the FFT of the envelope of the filtered signal. In this case, we can extract some periodicity in terms of modulation of the central frequency, in this case, the blade pass frequency. Please note that in stable condition, the FFT of the envelope present not a specific peak. In deep surge, what happens? The filtered content is characterized by a modulation at very low frequency. 5 Hertz. This means that there is an interaction between blade pass frequency and oscillation mass phenomena, and this interaction is also observable not in deep surge, but in incipient deep surge. See the upper spectrum. So with spectral kurtosis, we are able to separate deterministic from random contents. Inside the random contents, also the random contents not stationary, but the transient random contents. And this is very useful for surge detection. Spectral kurtosis was used on inflow pressure signal, but also using accelerometer signal. Accelerometer signal is more difficult as the structure acts as a filter, so is more difficult to detect the surge. Accelerometer are more simple for their application. This method works also using structural response vibration signal. I think it's all from my side. We used this method in a test bench, but also in real plant in particular on 2 fuel cell emulator with encouraging and good results, and publication are available. Thank you for the attention.
Thank you, Paolo. Thank you very much for your well-detailed presentation. So I would propose we would then move to the presentation of Sébastien, and then we gather all the questions to the presenters. So thank you again, Paolo. Sébastien, floor is yours. Thank you.
Okay. Can you hear me well?
Yes.
I will share my screen.
Okay.
Okay,
I see it.
Yeah, okay, thank you. Good afternoon, everybody. So I'm Sébastien Grégoire. I'm working for ENGIE, and I will do today an introduction to Robin, our historian for asset monitoring, with a use case on vibration. So this is the agenda for today. First, a brief presentation of the ENGIE company, then a chapter over our operational data infrastructure, some use cases, and finally the vibration monitoring, which is the latest one that we implemented. So ENGIE is a utility company and a leader in the energy transition. We provide energy to the customer in the form of electricity, heat, gas, and in some areas of the world, clean, sweet, drinkable water. The numbers that you have on the slides are from last year, so they have moved a little bit. So, for instance, the nuclear electricity has been divided by due to the closure of 2 plants in Belgium. The battery storage, we are more close to 2 megawatts. If we look at the renewable, so we are above 40 gigawatts of renewable installed, with a big increase in the coming years, with 4 extra gigawatts per year, and soon 6 gigawatts per year. So the target is to have 80 gigawatts at the end of 2030. The thermal capacity is around 60 gigawatts. And decentralized energy production on-site generation is around 25 gigawatts. The goal of ENGIE is to have net zero carbon in 2045. And to achieve that, we are structured in 4 GBU. And today I will mainly speak about the first one that you have on the slide here. So the renewable and the flex power GBU. Next to that, you have networks, local energy infrastructure, and supply and energy management. So if we go to flexible generation, We have there some challenges in the coming years. So first one is the BESS, so the battery energy storage system. And those BESS are driven by the big spread in energy price on short term. So you probably know it happens quite often that the electricity price are negative during the day when there is a lot of wind and a lot of sun, and then a few hours later the price are up again, so those BESS can profit from that by storing energy when the price of electricity is low, and then delivering the energy when the price is higher. H2, we are also active at a slower pace, but it needs to be monitored as well. The flexibility, it's also a challenge for us, because if you look in the past, the CCGT, so the classical power plant, the role of them was a provider of electricity, while now it's more a provider of capacity and flexibility to complement the renewables. That's the renewables that dictates the market, and the classical asset must be flexible to complement that. And as well, that's true for the grid. So the CCGT and other assets must be available to supply the grid capacity. So we need to be available when it's needed. You cannot grab the opportunity on the market if you're not available. So we need predictive analysis for that too. And finally, we need to capture value with AI. AI is quite new. We are using it more and more, and we will see in the future where AI will bring us. If we look at the landscape of our historian, so we are using the AVEVA Pi historian in ENGIE. So before it was AVEVA, it was Osisoft, so maybe you know Osisoft Pi. And we started in 2000 with the installation of a server in the Holland and in the Netherlands. And then from 2005 to 2010, there was a rollout in whole Europe. So the situation that you see there on the slide is from 2015, where we are, each dot is a Pi server. So we had several Pi servers, regional based or asset based. So it was on premise of the plant, or sometimes per country, but we had 15 different Pi servers. And at that time, there was a crisis in the utility lands. So a consequence of that is that the maintenance of the server was not done as it should be. So we had to find a solution. So in 2017, we centralized all the European server in one unique server located in Belgium. And so all the assets of Europe were connected to this unique server in Belgium. We saw, of course, the advantage of it from an infrastructure point of view. So that means one server, that's only one server to maintain. But the biggest asset value was from the user's perspective, because it was much more easy to share the experience between the different users, because they all had access to the same server and to the same data. So that led to the next step, which is in 2019, one server that was made available worldwide for all plants of ENGIE, and we branded this server as Robin. So when I will speak about Robin in this presentation, that's the name that we gave to our historian based on the AVEVA Pi. So I said it, the PyRobin is based on the AVEVA Pi. It is a software used to capture, process, analyze, and store any form of real-time data. And so today, you can see here some figure. We have 720,000 tags at the end of 2024. So that means 720,000 signals coming from sensor in our assets. We have about 25 years of the data, so that represents more or less 15 terabytes of data. Most of the customers are based in Europe, but we have also a customer in South America, in North America for some battery installation, in Australia as well for battery and CCGT, and also some power plants in the Middle East. So as you can see, half of the tax that we are using are coming from the flexible generation, so from CCGT main. So the concept, we get the signals from our assets, and they are going in real time in the Pi historian. I will go very quickly on those slides to keep in the time. So the signals are going into the Pi interface and Pi connector. They are stored on the server. Then we have also real-time analysis with some analysis in the Pi server itself when the data are coming in to create alerts in case of events or incidents, so that the experts are aware of it. And then next to that, we have different tools that are available for the analysis. So we use the Pi visualization suite, some KPI in Power BI. We have a Python library for the data scientist, and other tools next to that for the expert to perform analysis based on those data. So what do we do with all this data? We improve our performance, calculate efficiency and performance parameters. We increase the availability with condition monitoring. We get more value from the output by a reduction of imbalance and improve capacity forecast. And also we do some emission monitoring for to limit our impact on the environment. So I will now briefly show some concrete example. So the first one is performance monitoring. So here for CCGT, for instance, what we do here is calculate the efficiency of the complete cycles, but also from different equipment of the CCGT. So the steam turbine, gas turbine, condenser, pumps, compressors, steam generators. So if we see, for instance, reduction of the efficiency at the global level, we can dig in to see which equipment is the cause of it and where we have to look to find the cause of this loss efficiency. We also monitor the startup performance and the performance test. So that means what is the performance in the defined condition at base load of the unit. Another case is condition monitoring. In this case, in this screen for a feed water pump. So we monitor several KPIs. So for instance, here the performance, the cavitation, and the efficiency. And what you see here on those diagrams is that the black line is the curve from the OEM, so the specs of the pump. The orange line is the tolerance. That means what we accept without raising a flag. And the green dots are the real operation point. And so if we have a deviation, so if a point falls outside of the curve, then we create what we call an event frame. So that's created automatically. The concerned expert receives an email with this event frame and the reason of what's happening, and then he can easily go to this event frame and analyze what's wrong with the equipment and go further with the expertise and the solution. Another case is the DEMIN dashboard. So in CCGT, we need to produce some demineralized water. So for that, we have the DEMIN installation. And there we have also made a dashboard about the status of this DEMIN installation so that the operator can see if everything is running as it should, or if some maintenance is needed to improve the efficiency. So now I will focus for the remaining part of this presentation on the vibration monitoring. So I will start with a brief history of the vibration monitoring at ENGIE. So we started in 1985 with a system that was on premises, so on all the HP platform. So we had local storage and visualization, and the system was installed in the Electrabel plants, which is the ancestor of ENGIE. So it was only in Belgium. And then in 2000, we developed the Laborelec vibration monitoring system. So Laborelec is a subsidiary of ENGIE and is the research department of ENGIE, also providing support for operational excellence. And so we developed this system with remote capability. It was Windows NT based. And so already at that time, the expert could follow the vibration behavior in the power plant from their offices in Brussels, but also on the road with a GPRS connection. It was not very fast, but it was working. So it was possible to do all the follow-up remotely. In 2014, we developed a portable system for temporary missions. And at that time, the LVMS was monitoring a 80 shaft line of ENGIE, but also third company around the world. And in 2020, we replaced all the hardware of the 2000 installation with a new hardware based on National Instrument Compact Trio. But the software was still the same as in 2000. It has had some evolution, but the base was still the same, and so was not compliant anymore with cyber security stuff, and also to improve the software. So we had to do something to renew the software. And for that, we developed the Robin vibration monitoring, which is based on the data in Pi. And so we have there a web-based application for live visualization, and all the storage happens on the Robin platform. So briefly, a small crash course on vibration monitoring. So to do the vibration monitoring on fluid film bearing, you don't need a very high acquisition frequency. Of course, you need to do some signal analysis and FFT, but most of the case, so 90% of the case, can be analyzed by looking at the first harmonic component, so the component at the rotational speed. You look at the amplitude and phase of this component and of the second harmonic, the global value and the DC value of the sensor. With those information, you can solve 90% of the vibration analysis, and then you will need the FFT, the time signal in orbit for the last 10%. But most of the analysis can be done with those parameters, and those parameters can be stored in the Robin Pi historian. So vibration analysis, how does that work? You have here, for instance, a shaft with two sensors, two proximity sensors, and you see here one sensor that is called the phase reference with here a groove on the shaft, and the sensor will give 1 point per revolution to give the phase of the vibration, and so that the expert can know in which direction the rotor is turning. So when the rotor is running, you have this kind of movement, and so by placing a sensor at the bearing location, you can measure what is the movement of the rotor in the bearing, and the expert can then use this information to interpret the vibration. So what you see here is the orbit with the dot, the moment of the phase of reference. And if you place the sensor at a different location around the shaft line, you can then see the mode shape of the shaft line and go further, use it in your analysis. So in reality, a mode shape is much more complex than what we saw in the movie. So this is, for instance, a calculated mode shape for a steam turbine with two low pressure turbine, one intermediate pressure and one high pressure. And so why do we do vibration analysis? Because thanks to that, we can detect some problem like rubbing rotor stator, unbalance, coupling fault, alignment fault, bearing fault, and so on. And also generator short circuit, even if it's an electrical cause, it will have an effect on the mechanical state of the unit. And so you will see it in the vibration behavior. So let's come back to our Robin vibration monitoring. How do we use it? How does that work? We have on site the acquisition computer with here the acquisition unit for the signal, a small computer here that we call the core that will do all the data processing, will do also the alarming, will decide of the storage. And this core will provide an online HMI, so via a web page for the operator. So the operators in the control room or the plant manager at home on his computer can follow the vibration behavior. And then next to that, we store data in the Robin platform, and we have another HMI for the expert to do the analysis. So what does it look like? This is here a recording of startup of a unit. So what you see here above, that's a sketch of the shaft line with the amplitude in the bar graph. We have the linear diagram with some parameters. So here is the speed, the amplitude level of some sensor. You have the time signal, the FFT, the orbit that we saw in the movie. And here in the polar diagram, we see the amplitude and phase of the vibration. I will not explain today what's a polar diagram, but this diagram is the one that is used by the expert to analyze this vibration behavior. So the more far away you are from the center, the higher is the vibration, and the angle is in fact the phase of the vibration that we use for the analysis. So this is for the online interface. So this is what the operator can see in the control room. And then next to that, we have the offline. So the difference here in the offline, that's you see here the time bar. That show the operation mode of the unit. So in blue, that's the nominal speed of the unit. In yellow, you're on turning gear, so when the unit is not used. And in gray, when the unit is stopped. So we can see here a long stop period with an overhaul. So I can easily here select, for instance, all nominal regime during this period of 1 year, and after a few seconds I have the linear diagram with the trend of some sensor that I had pre-configured. So you can see here, for instance, that there is a change in the blue line and the magenta one, and so I can select those sensors and show them in the polar diagram. So in this case, I will have a look at what's happening during an acceleration before the overhaul with those sensors 5 and 7, and after the overhaul. And so by comparing both, we can see here, in fact, that the behavior of the cyan sensor before the overhaul is the one of the magenta sensor after the overhaul, and vice versa. And so, in fact, it's not really a vibration issue, but it's just that the INC guy has probably misconnected the sensor during the overhaul, and so swapped those sensors. And so this is already, I think, my last slide. And so thank you for listening. And Nicolo, I suppose that you will manage the Q&A for both presentation.
Thank you, Sébastien. Yes, I will send the presentation after our meeting. I will upload it on the website of ETN. So thank you for your presentation. So I would propose now to open the question and answers session. So whilst you are free to raise your hand and make any questions you may have, or also comments to Sébastien or Paolo, we also launched a survey on Slido to evaluate or to get your feedback on ETN webinars. So we see some questions in the chat and comments in the chat. So Higuang, you wrote a question, right? I could give you the floor, Higuang.
You are still muted.
Okay, so I think I can read the message. So surge can also be detected by monitoring pressure signals. How does your method using acoustic and vibrational signals compared with methods using pressure signals? I think the question is for you, Paolo. You can also...
Okay, thanks for this question. It's a very good question. As monitoring surge using inflow pressure signal is the best. However, it's expensive as you had to fix the probe and fix correctly the probe in order not to have Helmut's resonant frequency, which invalidated the measure. The inflow pressure signals is the best. However, we verify that also monitoring surge using vibration it is possible. Using vibration, we have to take in account that we have the structure, the dynamic of the structure, which interact with between fluid and sensor. However, it's possible to monitoring surge with vibration signals. However, it's more difficult the post-processing. As I said, it is good using vibration to observe the high frequency contents near blade pass frequency, and for example, monitoring and find modulation phenomena.
Thank you, Paolo. Are there any questions or remarks from the audience? Alberto, you can also take the floor when you want. I see your comment on the chat.
Thank you, Nicolò. Good afternoon, everybody. I have a question for Sébastien. I know, exchanging data with the real plants, whatever they are, it's always a very sensitive aspect. So I don't know how you face the cybersecurity and the safety of the control systems that are on site.
Yes, that's a very good question, and I'm not in the cybersecurity department, so I cannot give you a precise answer to that. So what I propose is that I come back to you later. I will ask to the expert because I prefer not say any dumb things today. I know that everything is secure and that we have a secure channel between the plants. But I don't know all the details. Sorry for that.
Thank you.
Thank you, Alberto. So we still have some minutes to go. Ian, please.
I'd like to thank both for the wonderful presentations. I have a question really aimed, I suppose, I'm spoilt for choice. I shall aim at Grégoire. I noticed that you seem to have a life of control system or life of data acquisition system of about 10 years. That's the time constant. So we have power plants there with 40, 50-year service lives, and you have to keep changing the electronic data collection and analysis system. And I suppose my question is how have you given thought to how we keep the history of the whole plant, even though we have to keep changing the electronic hardware during its life?
Yes, so if we speak about vibration monitoring, then there what we did is convert the vibration data in the different systems that were evolving over time. For the other equipment, so the Pi server is installed since 2005, let's say, in all the power plant. And so even if you change the acquisition hardware in the power plant, they are sending the data to the Pi server, which is the same since 2005. So even if you change the hardware acquisition, the way the storage place remains the same. So that means that we have 20 years of history of any data, even if you change the acquisition, because the storage remains the same.
Thank you. Appreciate it.
Thank you, Ian. We have another question from Hugong. This is a question to you again, Sébastien. Sébastien, does the diagnostic system provide root causes to the abnormal signals to customers?
I would say not yet. So we have no system that can give an alert when there is something abnormal, but we have a project using AI where the intent is to be able to pinpoint the root cause. So currently we have a lot of tools available for the expert to easily find the root cause, but we have not yet an automated system. So we are working on it, knowing that it will not be perfect. That's also why I say in my presentation, we will see where AI will bring us in the coming years, because with AI it's very nice on paper, but if you have a lot of false positive or false negative, AI can also hallucinate. So this is something that we still need to explore. So currently there is no system that can that can provide a root cause directly, but we are working on it to see what is possible.
Okay, thank you, Sébastien. We still have space for last, I would say, 2 questions. If the audience is still interested to get some further information or wants to comment the presentations of today. You can raise your hand or also write in the chat. Ian, please.
A quick one for Paolo. I'll happily follow up with you on this, but GE Aviation with, I think, the FAA under a US funded program called CLEAN, I think, did some gas turbine compressor surge prediction work, and a lot of that work was based upon Georgia Tech algorithm, and they're using some fantastic optical sensors, pressure sensors at 200 kilohertz to do it. But a lot of it was as you said, the complicated high-speed algorithm work was essential for that. So I can point you at that for that. I'll make a connection. Thank you.
Thank you for this observation. Surely to investigate high frequency contents is more promising to find useful information for instability detection. It is an additional information which can improve the diagnostic system, and so to avoid false positive and more efficiency in the anomalous condition detection. So I think high frequency range sensors are very fine for diagnostic purpose.
So we still have another question.
Well, there's a question there.
Yes, please, Wang.
No, not me. That is from James Dayton, right?
Yes, exactly. I was going to get there. So there's another question for Sébastien. So what is the driver for using an NI-based system?
Yeah, very good question. So we used the National Instrument acquisition card in the first system. So not in 2000, but from 2005, I think. And then when we had to upgrade the hardware, we have looked at the possibilities. So at ENGIE or Laborelec, we are not hardware maker. We use solution on the market. We can code something. We can assemble, but we are not making hardware. So we were looking at what is available, and the NI hardware is very robust. So there are not a lot of. We have looked at other possibilities, and there are not a lot of possibilities of an hardware that you can leave in a power plant without touching it, that can run years without any reboot or any failure. So that's the main driver. They are not the cheapest, but on the reliability side, we really have no issue with them. So we have if you go back to the acquisition card that we bought in 2005, 15 years later, they are still running. The compact trio that we are using now, some are running for 10 years without any issue. And so that's the main driver of using an NI-based system.
Thank you, Sébastien. I do not see any further comments. Okay, the last one from Martin.
Thank you, Paolo. I would have, also first, I'm Martin Henke from DLR Stuttgart. Paolo, I would have a question for your presentation, especially as we have heard from Sébastien today that there is a lot of proximity sensors being used in larger machines. I assume they have quite some advantages. Have you also considered if these sensors are applicable in these smaller turbochargers?
Surely, proximeter allow to extract information directly from the rotor, while accelerometer are fixed on fixed reference. So also in this case, as we have a mechanical system characterized by inertia, we have the convolutive response due to the presence of inertia. Surely, as use pressure signals is good as we are very near to the phenomenon, the surge, the fluidodynamic phenomenon. Using also information coming from proximeter can help to have additionally information in terms of dynamic response of a structure. However, for high rotational speed machine as a turbocharger compressor is more difficult to install proximeter for high frequency range. However, it would be an additional information coming, an additional output useful for the diagnostic purpose, the proximeter one, as it is direct the dynamic of the rotor without the fixed reference.
Mm-hmm. Yeah, I was wondering because you read a lot about this proximity sensors for larger machines, but I found nearly nothing for these sensors for the small machines. But yeah, I think you're right. Probably it's also because of the difference in speed. Yeah, that it's quite harder to get the information for such high frequency. So thank you.
However, if you are able to deconvolve the contribution of a structure, you can remove and separate the content in the accelerometer strictly related with the surge phenomenon. Our idea is to use the accelerometer and to deconvolve the signal, try to remove inertia, resonances, and other phenomena make it more difficult the interpretation of the acquired data. Surely a proximeter would be useful, give direct information.
Yeah, but of course the access is much harder to gain.
Yes, yes.
Interesting.
Thank you. Thank you, Paolo. Thank you, Martin. So we are slightly running out of time. So we'd like to close the webinar now. So first of all, thank you, Sébastien, and thank you, Paolo, for making it today, for presenting on digitalization of turbomachinery. I would like to thank all our participants to attend our webinar. And we look forward to hopefully seeing you in person in 2 weeks' time from now at the annual general meeting in Norway. So thank you very much and wish you a good day.